our next speaker is Dr. Birol Dinodruk from Shell. He is a chief scientist and principal technical expert in reservoir engineering at Shell International since 1997. He is a member of National Academy of Engineering, an adjunct faculty at the University of Houston, as well as Stanford University. He is currently the editor-in-chief for the Journal of Natural Gas Science Engineering and a member of the Society of Petroleum Engineer Board, serving as technical director. Let's welcome our second speaker.
Thank you, Dr. Lee. Good morning. First of all, I thank the organizing committee for their kind invitation. And the talk that I'm going to give today is going to touch many of the things that was highlighted earlier at the introduction by Dr. Lee, as well as the previous Dr. Waddell as well, previous speaker. I will hit a number of key points over here and try to see what the energy mix and its implications will be, and also current state of affairs. Let's see. Well, I have to show this thing because of my affiliation. I don't expect you to read it. So anyway, don't believe in everything that I say. Okay. The first thing that this is the outline actually, but the outline, I try to make it as granular as possible. However, many of the things and points that are highlighted here are interrelated. So I'm going to be going back and forth between those elements here and see where we go. And hopefully I'll finish it on time. Well, I mean, this is already highlighted. If you look at the mass of all the living creatures, we are one of the smallest ones, so as to speak, over here as humans, but we have the greatest impact on the planet. So you can see animal world, we are a minor fraction of the entire thing, yet our population is increasing, so it's creating a lot of implications. We have also bad habits as well, actually. We burn fossil fuels, we generate, CO2, etc., but we also, whatever else we do can lead to other things as well. This is an interest. It's a very long article, actually. You can look at the original one as well. This is just one of the snapshots, actually. Plus the transportation, right? We also transport the food as well. But the bottom line over here is this. I'm not going to go into the details of human diet, et cetera, over here. You can read it, actually, which is quite interesting. Plus, if you look at some of the habits that we have, we also generate greenhouse gases, not only CO2 equivalent, we also generate methane as a byproduct, for example, farming activities that we have, various activities that we have. But the bottom line over here is that energy per use per capita is related to Human Development Index, actually. So basically, energy is a vital part of human life. It's related to health, security, feeding ourselves, etc. So in fact, it has three elements: improving human life in terms of economy, environment, and social development. So also it's correlated with energy use, is correlated with the GDP and the prosperity of the nations. Of course, there are anomalies, scatters, etc. I mean, every single point over here is worth for special analysis, which is already covered in the given reference here. So it's a challenge for us. We want cost-efficient energy systems, much lower emissions as a result, which is the environmental security part or environmental aspect of it, and also energy security. So multiple options, and we want robust and resilient systems. So, of course, the opportunity is to create and manage linked complex systems that deal with all these challenges for us. So the problem over here is not one isolated case. The scale of the problem is the issue, actually, which I'm going to highlight. This is already highlighted earlier in a certain level over here. But if you look at it, this is our shopping cart, so as to speak, actually. What energy resources can we use? We can spend a lot of time on this thing, but for various reasons, we are focusing on a subset of all these resources over here that are available to us. A lot of, in the energy mix, as is evident and documented in many places, fossil fuels are leading the pack over here in many ways, depending on the use cases, of course. But of course, the use case of the energy is related to many other things: convenience, energy density, portability. It has many other dimensions, actually. But this is just to highlight what happens in the context of what we select from the shopping cart, so as to speak. I mean, of course, it's not something that, when I say shopping cart, it's not necessarily by choice, actually. It's an evolutionary process. And I'll show you some elements of it. In the meantime, as we use energy and as our consumption goes up per capita or overall, things change over the time as well. And there's always continuous research and development and efforts that we have, that we try to predict the future. What's going to happen next? What are the trends? How are we going to deal with the future? But today's energy mix, if you look at it, so, you know, if you look at the subcategories in terms of sector and consumer trends, we see three elements over here. Domestic and commercial demand is one part of it. The other is transport and industry or industrial applications. If you look at, of course, if you look at the transport sector, 96% is related to liquid fuels, whatever the origin might be over here. So depending on the application, substitution of energy from one form to another could be easier or more difficult. For example, if you want to apply some of these things in a more portable form, you can't carry around big installations, and also how you would refuel. So these are some of the limitations. But when we look at it for the cost efficiency challenge over here and the general usage, we use quite a bit. This is the US statistics, transportation, industrial, and also commercial. And also this is the what is the percentage that we spent in terms of GDP. If you look at it, the percent of gross domestic product, according to IEA, we use about 6 to 8% of GDP in the US. And if you do it in the ballpark calculations, we know the world GDP actually, and it's about $10,000, $12,000, and we know the world population. And we know how much oil produced per day, and you can even calculate how much oil per capita is used, as well as you can look at the energy density of it, and also you can ratio it to GDP. We know the nominal oil price for a given year, at least on the average basis. You can also calculate what would be the GDP for that year. Of course, when the energy prices are high, that ratio goes up. So energy cost-efficient economies are competitive economies, actually. So it's the essential ingredient for any economy. And the technologies compete in a commodity price world. So it's not, cost is an integral part of our choices as well over here. But of course, scale is another issue. You will see in a little bit some of the elements of this. So scale of the problem, when we look at it, and when we look at the population increase, is a big challenge. If you want a steady state or stagnant population, the fertility rate is little above 2, actually. Right now, worldwide, the number is 2.51. So that means that every nation wants to be more and more prosper and lift the life standards of their people. And when you do the math over here, this is the growth model, at least for the next decades here. And right now, for about 4.5 barrels of oil per person, if you just divide the entire production by number of people. But of course, we have been predicting these kind of numbers for a long time as well. I'll show you what kind of predictions we had. This is the same thing again. I repeat this plot. And in fact, if the population and development challenge is very big problem right now, and if you look at it, the increase in world population, this has a lot of assumptions, but the final goal is over here is about 1.8 children per woman. So, and our energy consumption aligned with this, and the prosperity of the nations is going to increase. Of course, we need to fill this gap. The energy over here is related to many other things as well. One of them is this is about electrification, impact of it. And the other one is the information technology. If you look at it, our industrial productivity or labor productivity is going up with, is aligned with energy use or electrification in this particular case, as well as information technology. It's a scale plot, of course, but it's very important element over here in terms of the role of the energy. And the challenge over here is, again, 7 billion to this 2015 to 10 billion, and increasing demand over here, 570 exajoules to 1,000. It's all aligned with these numbers. And, of course, CO2 emissions is increasing as well. And, of course, our goal over here is net zero emissions. Of course, as we have these challenges, our habits are also changing. Our behaviors are also changing in various ways. I'll show you a couple of them. For example, one of them is this. If you look at it, this is prediction. We'll see actually whether it will hold or not. But if you look at the demand for energy for heating, it's stagnant. But as we get more prosper, the demand for air conditioning and energy spent for it is quite significant if it holds, actually. So, you know, it brings more demand in a different way. We may be conserving energy in one area while increasing in the other area, actually. Of course, efficiency is the first thing that we can do over here. Of course, with the Internet of Things and new sensors, and you know, many of us over here, if you upgraded your air conditioning system or heating system at home, you can manage it from a cell phone, real time, pretty much actually. So what it means that some of the measures and some of the lined up developments are leading to the conservation over here. So smart systems, smart grids, smart homes are just part of those. And, but if you look at the historical predictive capability of what we have, when I was undergrad, once upon a time, everybody was saying, we're going to run out of oil. What are we going to do now, actually? I mean, there were like doomsday scenarios and those kind of things. Everybody was predicting the peak oil. When are we going to have the maximum, the peak oil? Then it's going to decline the use for various reasons. But if you look at, in fact, it's very well known. It's called Hubbard Curve. King Hubbard's curve, actually, a bell-shaped curve in the industry. And as a matter of fact, if you Google, you'll see derivatives of it in many other areas as well. But when we look at the Hubbard curve over here, this is the updated one, of course, with respect to his original document, which has been some time ago. Every time when we have a local peak and a decline after that, we thought that, you know, we are resource limited over here. And if you look at the last spike in this curve here, I don't know, I can, oops. If you look at the last steep spike over here, that's the so-called shale revolution, actually. These are the contributions of, it's coming from contributions of the unconventionals. Another one over here is called Fisher-Price model. They were claiming, when I took some of the classes during my undergrad and grad years, we were saying that there are models that they can predict the market share of various elements of energy, in fact, the energy mix itself. But when we apply these models and when we updated them, none of them really hold, actually. The mix itself is evolving on its own. Of course, there there are economic aspects of it. When it comes to whether fossil fuels are limited or abundant, it's abundant, it's endless as a matter of fact. The key over here is the price, and it's true for many things. And this is another prediction that they had in 1980s actually, per capita. This wasn't so bad actually, per capita consumption in terms of oil consumption per capita is about 4.5. So this wasn't as bad actually, but percentage-wise it's about 50% off. So we keep predicting all these things and none of them are right actually. So, and what changed recently on this? When we look at the fossil fuels, the amount increased tremendously actually. You know, we had the perception in 1997. If you look at 2007, 10 years later, the circle becomes bigger. And mix, give or take, is similar in general terms. There's no step change, but of course, in the mix, gas is increasing. Another, this is the current outlook towards the future as well. One of them is that global GDP is doubling. That means per capita energy consumption is going to increase. Maybe in some places it may decrease, but where the population is, per capita GDP, as it increases, energy consumption is going to increase. And current oil and gas is 55% of the mix over here. So what's going to happen is that I will show you other plots over here. In the mix, share of fossil fuels will decrease, and it's going to be offset by other energy sources, renewables and alternative energy sources. But the overall demand for energy is going to increase. While the market share of the oil and fossil fuels is decreasing, the total is going to be either constant or will decline. But the use case, I'm not saying, and I'm not necessarily saying that the fossil fuels will be used for energy. And I'll show you a couple of numbers over here. The key, the non-combusted part of the oil in terms of chemicals or other things, because oil and gas are raw materials at the end of the day, that segment is going to increase. That's the right direction, as a matter of fact. I mean, burning is a waste in many ways, and of course it creates many other problems in terms of global warming. And it's beyond that, actually. I'll show you a couple of other slides on that one. So I mean, these are some of the, these are highlighting some of the points that I already mentioned over here. The total is going to increase. And if you look at the green segment of the bar here, oil, for example, just take oil as an example, market share is going to be decreasing, while in absolute numbers it's either stagnant or the same, but gas is increasing for sure, actually. So, and this is another, this is a plot that I was playing around with the data and I came up with this one. The y-axis is market share function, and the red is the ratio of market related to the market share of oil, and this based on demand and supply. And the other one, the blue, is the coal, and the green is gas. So if you look at it, gas market share of gas is going up, independent of oil and gas. And if you look at coal and oil, they are almost like mirror image of each other, actually. In fact, when oil price goes up, coal consumption is going up, because everybody wants to conserve, basically, because you know, if you make oil or fossil fuels 150 barrels, $150 per barrel, it has wide implications for budgets of many places in the world. So people switch to coal somehow. And of course, one of the reasons that the gas market share of gas is increasing is, and it's the rate of increase is going up as well, is the gas that we are getting from the unconventional resources like shales, etc. So if you look at global unconventional gas, of course, gas is preferred with respect to, it may not be the best, but it's preferred to liquid fuels or crude oil itself, because it has a lot less impact in terms of greenhouse gases and emissions, and much cleaner. And also the distribution of unconventional gases more scattered around or better distributed than conventional hydrocarbon deposits that we know of. Of course, in a commercial scale, if you look at any kind of hydrocarbon show, probably you can find it in any place, but in terms of producibility, they are limited. And I'll skip this one. The transportation sector, of course, there are other things going on over here in terms of our habits, I would say, or lifestyles. One of them is the air transportation. The passenger numbers are increasing tremendously, 3.5% annually. If you look at the jet fuel, if the predictions are right, it's going to be about 16% of the entire oil production per year with this growth rate, which is about 16 million barrels a day, give or take. And of course, the electrical vehicles are increasing over here. So of course, we need to source those in a sustainable way, maybe biodiesel and other things. But the rate of increase is quite high. And as I mentioned earlier, the non-combusted use of oil and gas will increase by 20%. So it's going to lead to about, at the end of the day, about 45% by the year 2040. So what it means that, if we are not burning the fossil fuels, we will automatically reduce the emissions as a result. So global market for chemicals is growing as a result as well. We have huge demand for composites and new materials, plastics, etc. And recyclable, many of them are recyclable. At least there's global effort on recyclability. So that's the good news in terms of the production, the use case, from use case point of view, actually. And the emissions as a result of gas power plants, et cetera, and the role and the market share of gas is increasing. The increase in CO2 emissions are reacting to that as well. But of course, there's still issue on it, obviously. Renewables share is going to make up the difference in terms of demand and supply as we go on to the next 2 decades. So we definitely need to increase those efforts, actually. This is the increasing renewables in power generation. And in many places, there are a lot of coal-powered plants are going to be decommissioned. If you look at over here, all the red bars over here will be decommissioned, at least destined to be that way. And of course, there is one energy source that was mentioned over here is a geothermal reservoir. Some of the energy can also be, and it is being generated from geothermal resources. This is the schematic of it, basically. Surface waters are going to places, certain places close to the magma and heats up, and we can extract that thing. And the interesting thing is that geothermal potential is in places that they really need the oil or energy. So it's a little better from that point of view. And it's in commercial scale, it's applied to a number of countries already, like, for example, New Zealand, Iceland, Turkey, Italy, California, geysers. And there's some development for it as well. Conventional steam turbines operated historically at much higher temperatures and higher steam richness. Now, there are binary power plants. We use different working fluid for them. They are a little more complex. And it's possible to operate them at a lower temperatures over here. Also, there are other developments in geothermal as well, actually. That's why I brought it, thermoelectric power generation. Especially when we have on-demand systems with sensors or low wattage requiring devices that require energy at all times. For example, geothermal power generation in this context could be quite useful. It's a solution. It's a distributed solution. It applies, I would say, where it applies, wherever the hotspot for it is. But in fact, there are new papers. I didn't read all the newer material on it, but I was visiting Stanford 2 weeks ago. I've seen benchtop TEG device that they have actually. So it's a coupled device. They were producing with this one. I can't remember. It's like maybe 80 watts or something like that. I can't remember all the details. It has bulbs on it that just for the showcase and all that actually. So it's it doesn't require very large temperature gradients actually. That's the good news. So at least it can be useful, and it's 24/7. It's not like solar and other things. Everything helps. That's what my main point over here is that, okay, when it comes to, okay, what are the drawbacks of these things? Right now, the current energy mix is creating a lot of trouble, beyond trouble for us, actually. If you look at the plot, this is from the ice cores and various places, actually. This is thousands of years before present. Present is what you see, that little spike, basically. It's quite fast. And in fact, the latest update is 411 ppm, or 411 ppm in January 2019. So I look at this beyond climate change, because what would be this is a chemical change. What would be the implications? What would be the implications for oceans, other living organisms beyond just the global warming? It's one of the symptoms of it, of course. So there's definitely need for change. So of course it brings us to the subject of carbon capture, utilization, and sequestration over here. So if you look at it comes from many places, but I'm going to focus on more over here in sequestering CO2 in geological formations, because it's a proven technology. There are a number of projects in commercial scale ongoing in the world on this. So this is the schematic diagram for CCS systems. And once we can separate the CO2, we can sequester it in geological formations. But of course, if we can convert CO2 into other things, which is in the previous chart over here, of course, I would say so be it, if it applies. But when you look at the scale of it, it's huge, actually. So the geological storage potential is tremendous. It includes depleted oil reservoirs, depleted or deep saline aquifers, as well as unminable coals. And in fact, right now, people are bringing unconventional resources or shales. And even volcanic rocks are brought into the picture as well, because we want these things to be as distributed as possible, actually. I mean, you don't want to make a special pipeline to transport your CO2 to a point that you can sequester. The more variety we have, the more distributed it is, the better it might be, actually, because it will cut some of these frictional cost elements for us. These are the storage opportunities, as you can see here. It doesn't include all the potential for volcanic rocks, etc. Mineralization of volcanic rocks is another way to sequester CO2. So this is based on proven technologies, actually, if you look at it. And in Shell, we are part of many projects like that, and right now we are scoping many of them as well. Capture is a proven technology, solvents use. Of course, there's opportunity for improvement for every element over here, but at least it's something that we can do today. Transport, we have pipelines right now, 6,000 kilometers of existing CO2 pipelines. Of course, they are done for other purposes, but they can be easily repurposed. Storage, we know the subsurface quite well. I mean, we have expertise, especially when it comes to depleted oil reservoirs or hydrocarbon reservoirs. They are well studied for a different purpose. So if we already know something, it's a lot easier to put the things back over here. It's essential for heavy industry as well. So some of them are already implemented. For example, CCS over here is already applied in commercial scale. And there are two other applications of it in UAE for iron and steel, and ammonia in the US. So it can also create new jobs as a result as well. These are the potential job creations in Europe, basically. So these are options. I'll mention a couple of them. One of them is, of course, using CO2 to recover oil. or other hydrocarbons. So basically, you put the CO2 back before you use it, as long as you don't produce it back. So that's the thing. So you need to repurpose that element here. It could be enhanced coal bed methane recovery. So CO2 will displace methane, but you can pack a lot more of it. Of course, deformations with saline water and unminable coal seams. We have quite, in the oil industry, we have a lot of experience in producing and injecting materials into natural occurring porous materials in large scale. Those are the reservoirs, basically. So that skill is essential to manage and implement these projects. So this is the schematics for enhanced oil recovery. I will skip this one, actually. One of the things that we have already infrastructure for injecting CO2 for a different purpose. Now we can inject CO2 for not to produce hydrocarbons, basically. So that's what the main message over here is. Of course, when you inject CO2 for deep saline aquifers or unminable seams or shale formations, etc., you create other types of problems over here. First of all, would you be able to predict the fate of it? You need newer numerical models, mathematical models, and research. So that's an area for development as well. And of course, we want to evaluate the projects before we implement them. And I'll skip this one as well. We are involved in a number of CCS projects in different phases, and they're all different phases of development. We have projects in operation already, like Quest and TCM. And we have projects under construction, Gorgon project in Australia. We are part of it, Pernis Refinery, and we have Clean Gas Project, Northern Lights, and various other projects. And we are continuously evaluating synergistic sequestration. For example, if there's a refinery, how you can get the produce greenhouse gases and sequester somewhere close by, as close as possible, or if there's a pipeline or infrastructure, how we can implement it. And of course, the deployment needs to accelerate over here. We need to, these are mega scale projects. And of course, CCS requires other elements over here. One of them is policies and project characteristics. And of course, some countries already reacted for enabling policies. For example, US has 45Q tax. In fact, the credit increased in the late years. Canada has carbon price increasing to 50 Canadian dollars per ton by 2022. Norway has a tax on oil products. And our ambition is to reduce and basically get rid of the net carbon footprint. And these are, again, the existing examples towards that direction: flare reduction, increased LNG, wind power. We have groups in Shell working on all these elements. Not only oil, I mean, we don't only work on fossil fuels, we work on many other things, clean energy initiatives. And this is also, of course, electrification aspect of it. We also we also acquired companies that are that can charge. They have stations, EV stations. Especially with this growth rate, we need more of those. And I'll skip this one. Of course, drop-in fuels will greatly ease the transition over here. Very low cost, clean energy, and a lot of R&D to lower the cost actually is needed. So this is forward-looking. Long transition here at the very last. So this is going to be multidisciplinary, multi-country, everything, all of the above kind of initiative, because scale is big, and it's at the end of the day, it's our planet. And this is already highlighted earlier. I won't go into details, a lot of details on it, but lots of better research. One of the issues as highlighted is the peak tapering over here, how you can get something in on demand, and how you can taper the peaks, basically, and how you can store it. Storage is one of them. Still relatively expensive compared to other options. Of course, this is the power value chain for us. We need to work on the customer side of it, optimization side of it, as well as supply and generation. And the pace for decarbonization will vary by industry sector as well over here. For example, the buildings, etc., are easier. Industry is, in a way, easier in terms of the generation part of it. But transport is going to be more challenging, especially for planes. But more difficult to decarbonize those, actually. Okay, we can substitute fuels from biological resource or other from other sources, but it's difficult to, for example, sequester what comes out of them. And this is also another impediment to the progress in many ways, because these are the infrastructure turnover in years. So it's going to take years. I mean, these are big capital-intense projects, actually, if you look at it. I guess the easiest appears to be the lighter vehicles over here. And of course, the journey to net zero emissions requires a multidimensional approach over here. One is the technical, the other is the policy-related and regulatory drives over here. Of course, some of them are from the commercial drive point of view. If you look at it, advanced batteries and solar fields are ahead of them. In many ways, if you look at it, the economy or the entities may move in the direction of money, but the regulation is going to bring the yardstick for everybody, so as to speak. And long distance transport will still need liquid fuels for the time being. This is the last element over here. And we have programs to tackle many of these challenges in Shell. We have programs in dense energy carriers, advanced energy storage, methane to products. So we have enabling capabilities right now in groups intensely working, large groups on computational material science and chemistry, biosciences and bioengineering, and exploratory experimentation. We have 3 different research laboratories, one in Houston, one is in Amsterdam, the other is in India, Bangalore, basically. So we have wide-scale initiatives. These are some of the places that we have such activities. We also sponsor small companies as well, or startups for some of the technologies, not only in-house. And we are working on high-throughput virtual screening of long-term growth and also advanced molecular modeling. Those are for new materials as well as the batteries and materials for batteries. And in summary, the current trends in energy mix is changing. I mean, as seen, energy density storage and peak demand management are still key issues, but also, of course, these issues are also opportunities. Shell aims to become a global leader in cleaner and power generation, taking advantage of our global footprint and experience with large-scale power infrastructure. Natural gas and energy storage solutions must integrate renewables to meet the new energy needs and growth, customers' demands as well. So Internet of Energy, more connectivity, which will help in load balancing where it applies. Of course, new business models will emerge due to digitization and interconnectivity, one world type of situation. Cost and scalability will still be the key factors in the context of implementation. So the bottom line over here is the enabling technologies are also getting cheaper to help us. Thank you.
Thank you, So I have a question. So I think there's a huge transition from fossil fuel to energy to fossil to materials, right? So because you have a huge economy and you have people who needs to do this transition from energy to materials. So how quickly do you think new materials, which probably replace certain construction or building material, how quickly do you see this transition happening realistically speaking?
I think it's going to take, realistically speaking, decades actually, because the scale is very big. Local applications will be a lot faster. I always use this language. It applies where it applies. If you have, if it makes sense economically, maybe with the tax credit, etc., it might be local, but global scale is going to take decades actually. I mean, we have many of the things that we do are incremental at the end of the day. But of course, there's always chance for disruptive technologies, actually. So those are the things that can accelerate things for us.
So because of that, then probably carbon sequestration, which you spend quite a lot of time on, is definitely needed.
Yes. I look at the problem like that. It's a big problem. It's already highlighted, and I have shown the CO2 amount in ppm. I mean, it has wider implications than even climate, actually. It's scarier than that to me, personally.
Ocean acidification and all
yes,
kinds of...
all sorts of planktons, and you know, they are lungs of the world, and all that, actually. I mean, I didn't have time. This is a cross-sectional kind of a presentation. But when I look at it like this, right now, there are proven technologies. We have to start now. As we go, if we find something better, we can switch gears, actually. That's how I look at the problem. I mean, okay, we can scratch our heads until we become bald, so as to speak, for next 20 years, what is the best, etc., and the cheapest, but 20 years is 20 years. I mean, as you see, the CO2 emissions and the world population and energy demand is increasing, and still fossil fuels are a big part of the mix over here. But of course, there's the good news on that one. More gasification, more gas, as well as the production that we see is not all burned, actually. So the share of production in the context of like the non-combusted part is increasing, like chemicals, demand, etc. So those are the good news. But our habits are also getting going for the other side, I would say. On the negative side of the equation, like as we become prosper, we put more air conditioner. Like everything becomes electronic, has also a cost, right? I mean, every little device has also consumption. When you add it up, what it could be.
And things like that.
Yeah. I mean, there are pluses and minuses in those things, but my point is that right now we have all these depleted oil reservoirs, for example, as well as deep saline aquifers that we know. We have the technology. We could start burying it as we speak.
Hello, Professor Niju, we are already late for 10 minutes, so
okay.
We no more KOA, so but you guys can discuss on a coffee break. The coffee break on the third floor, one more floor. Yeah. Come back at 11. Come back at 11. Yeah.
Okay. Thank you very much.